When dust clouds rise in the atmosphere of a brown dwarf or a hot exoplanet, particles collide, rub against each other, and become charged. Static electricity can arise from friction, heat, and even light when ultraviolet radiation knocks electrons off the surface of dust grains. This process is especially active when the particles are irregular, not spherical, but needle-like, jagged, or fractal in shape. And then, electric charge begins to accumulate at the tips of these microscopic antennas. Around them forms ionized gas. Dust behaves like tiny floating electrodes in plasma. Electrostatic instabilities emerge, slow, wave-like redistributions of charge that produce not lightning, but soft flashes within the plasma. But when the charge becomes too large, real lightning forms. A discharge through the cloud. Breakdown. Light. We already know several worlds where conditions for such weather may be ideal. 55 Cancri e, a hot super-Earth, possibly with lava oceans. Kepler-10b, a lava desert. Kepler-186f and Kepler-62f, rocky planets in the habitable zone. HD 189733b, a hot Jupiter where SIO bursts have been detected, likely traces of lightning. Lumen 16b, the nearest brown dwarf with a highly dynamic atmosphere. Just imagine. On HD 189733b, estimates suggest up to 1 million lightning flashes per transit. That's one every 0.01 seconds. Lightning is not just a flash. It is a chemical laboratory. It can produce molecules such as HCN, NO, and even precursors of amino acids. Lightning on exoplanets may be an indirect indicator of life. It creates its own spectral signatures, and if a telescope detects them, we gain a window into an alien world. And in that world, there is dust, light, and electricity. We are only beginning to study electrical weather on exoplanets, but it may become one of the key clues in the search for habitable worlds. And this is not fantasy, just physics.